Okay, so what I'm going to do, I have a PowerPoint, but then I'm going to have a notebook open to go through the problems, so Sammy can see the work that we work out. Okay. So, work. You all have taken physics of some fashion. What do you know about work? That's all you know is joules.
Newton meters.
F times delta X.
Newton meters.
Yeah.
Yeah.
Force times displacement.
Yes. Newton meters.
Okay. So work equals okay. So if we have a constant force, our work is just force times displacement. For example, okay, Isaac weighs 150 pounds, and if I lift Isaac, because I'm very strong, off of the ground 2 feet, right? Then I am doing 300 foot-pounds of work.
Guess my weight. You just guessed it right on.
Yeah?
That's weird.
Guess my weight.
You really want me to guess your weight?
Yeah.
125.
No.
Oh.
Then I don't know. Am I too low or too high?
Too high.
115.
Some days.
118.
Yes.
Okay. Here's the here's the trouble though. We don't always have a constant force. Okay? For example, if I am pulling up a rope that is hanging off of a cliff, as I pull up the rope, it is weighing less and less each time. Do you agree? Isaac's not changing weight when I lift him up. Okay? But, okay, let's say like a chain. All right, a chain's a little bit heavier. That might be easier for you to visualize. But if I have this chain dangling off a cliff, as I pull it in, it weighs less and less and less. So our force is constantly changing. Okay? So we're still talking about force times displacement. However, we're going to have to use an integral to account for those varying forces. Okay. Now, you guys have the advantage of knowing calculus while you do physics. Okay? When do you talk about Hooke's law?
Last year.
Last year at what time? Beginning. Okay. So you didn't know calculus when you did Hooke's law. Not enough calculus. Okay? Hooke's law is actually based off of calculus. And what Mr. Marsh probably taught you is how to do Hooke's law without having to do the integration involved. Okay? So the way we are going to do Hooke's law is actually simpler because we know how to integrate it. Okay? So, Hooke's law, the amount of force it takes to stretch a spring is proportional to the length that has already been stretched. So we have this equation, force equals K times X, where K is that constant of proportionality. So what we actually get to do is we can find the constant of proportionality and then come back to this right here, and we can plug Kx into this integral and just take the antiderivative, evaluate it from a to b, okay? Which is what you're doing when you do the 1/2 Kx squared, right? Okay? All right, so a 2-pound weight stretches a spring from its resting length of 1 foot to 1.5 feet. Find the work it takes to stretch it from its resting length to 1 foot 9 inches. So write down what you need to write down. Okay. So we have a 2-pound weight, which stands for what? The force, okay? So our force is our 2-pound weight, okay? And this 2-pound weight stretches it from resting to how far? Okay, so how far is it actually getting stretched?
6 inches.
Okay, half of a foot. Now, this is going to bother some of you, but since we're dealing with feet, when we look at work, we're going to get measurements of foot pounds instead of newton meters. Okay, every once in a while we'll get some newton meters, but if we have feet and pounds, we're going to get foot pounds. Okay, all right, so it takes us, okay, f of x equals kx. 2 pounds stretches our spring by half of a foot. So our constant of proportionality is 4. So we have 4x is our force, and since it's a varying force, we're going to integrate it to account for that varying force. All right. Now we want to know how much work is involved to stretch it 1 foot 9 inches. So from 1 foot to 1 foot 9 inches. So what would our limits of integration be?
0.
Because 9 inches is what it's getting stretched from original length, 3/4 of a foot. Yeah. Because that is the way that math textbooks are written in America. You would not be able to understand it.
Well, all we need is the numbers. So I mean,
Well, not on a problem like this.
I
We
wouldn't
need
be
to
able
know
to
the words.
understand.
I guess it's true.
I think it's French.
Oh, I see French 4.
Oh, well, I heard the French. Okay, so antiderivative.
I don't.
From 0 to 3/4. How much work is it taking? Foot pounds. Okay. Yes. So it needs to be like this because we're going from resting to 9 inches more. Okay. So since this, we basically don't take into account how long the spring is at its resting. Okay. Yes.
Do you know why pounds is ODS?
No. Do you?
No, it's something to do with
Okay. Probably a language that's
Or no,
not English. Now, if I asked you how much work would it take to stretch this spring 9 inches further, what would our limits of integration be? 3/4 to 1.5 would be your limits of integration. If I say 9 inches further from this, then we're saying, okay, well, we've already stretched it 3/4 of a foot, so that's where we're going to start, and then we're going to stretch it to 1.5. Does that make sense?
Subtract the first one.
Good.
If you did 0 to 1.5 and then subtract.
And then subtract the inch, so that would be fine too. Okay. What?
Libra.
Hmm.
That's Latin.
I say definitely language, not then what was I gonna say? Okay, so Hooke's law, and you guys have all worked with Hooke's law, yes?
Yeah.
Okay. No, we didn't. Oh, so you're doing Hooke's law right now?
Not yet.
Not yet. You'll get there.
That feels like the second middle reading.
Okay, so you're not the.
Like very, kind
Yes.
Okay.
But from the.
So Hooke's law also works for compressing as well as stretching springs. Okay. All right. Next, my chain example. A 40-foot long chain weighs 80 pounds and is dangling from the top of a cliff. Find the work required to hold the chain to the top of the cliff. So write any information you would like. Definitely 40-foot chain, weighs 80 pounds, work to pull it up. Whatever you need to write. But I want you to be able to look back at your notes and know what the heck the math was finding, right? Okay, so what do we need to take into consideration?
The fact that it's getting lighter.
It is, okay? So we know we have a 40-foot long chain that weighs 80 pounds. What does that tell us?
It's 2 pounds per foot.
Very good. Our chain weighs 2 pounds per foot. That's important. Okay? Okay, so 2 pounds per foot, all right? So what happens is our change in force, right? Our force is constantly changing, okay, is going to be 2 times whatever the change in y is, okay? Now we know that work is force times displacement, okay? Now we need to account for the displacement of this chain. So we have a cliff, and we have this chain hanging off, right? So at any given moment, why did I label that dy instead of dx? Okay, because we're talking about vertical movement, all right? So at any given moment, how far is the chain dangling off the cliff? 40 minus y. Why do you say it like that?
It's initially 40.
Mm-hmm.
Getting smaller.
Okay, it's initially 40, and we're pulling it up. Okay, so we have to subtract the amount that we're pulling in, right? Okay, so work. We are going to take the integral from 0 to 40 of 2 times 40 minus y dy. So we have our varying force times the distance that we have to pull it up. Okay. Why are the limits of integration 0 to 40? Okay, where our chain, it's all the way to 40, and then we're, pulling it all the way in. Okay. If we think about units here, let's see. We have pounds with 2 pounds per foot, right? Times feet. Times our very distance. Okay. So in the end, we're still going to get foot pounds. Okay. Now, can we integrate this one by hand? We can. All right. It's not bad to do by hand. Now, I don't really. So we're weighing 2 pounds per foot, and then we're accounting for the different distances that we're pulling this up, okay? And then we're adding up all of those different distances times how much the rope weighs. Does that make sense? All right. You will have a problem like this, more than in just your homework. Two problems. So it'll probably take us to the end of class. Write down any information that you need to. So we have a 5-pound bucket, raised 20 feet. We know the rope weighs 0.08 pounds per foot. The bucket starts with 2 gallons, but is empty by the time it gets to the top.
That's a lot changing.
Okay, so we have more than one thing changing, right? What all is changing?
The amount of water and just the amount of
The height.
Okay, so our rope is changing as far as like how much it weighs as we bring it up, and the water inside the bucket is changing, and so that's affecting the work that's being done. Now, what remains constant?
the weight of the bucket.
The weight of the bucket, right? So we have to account for 3 different things right now as far as when we're calculating work. We are pulling up the bucket, we are pulling up the water, and we are pulling up the rope. Okay, so we have 3 different calculations here. Okay, so let's start with the easy one. The bucket. You told me that it is a constant, right? How much does the bucket weigh? 5 pounds, and it always weighs 5 pounds. How much are we lifting it up?
20 feet.
So 20 feet times 5 pounds. It takes 100 foot-pounds for us to lift up that bucket of water. Okay. The water. How much does our water weigh per foot? How'd you get that?
16 by 20.
Okay, we have 16 pounds of water that dissipates over the 20 feet, right? So our water weighs What?
It wouldn't, yeah, because we're not.
Okay, what is our displacement of this water? Okay, so how do we describe at any given moment where? Okay, so our displacement is 20 minus 1. So in order to calculate the work of the water, we're going to have to integrate from 0 to 20 of 0.8 times 20 minus y dy. Okay, so here. So what do we have? 16 y minus 1/4 y squared from 0 to 2. 0.4. I'm gonna say 1/4 doesn't sound right. Oh, 20. I was like, 2. This does not make sense. Okay, what do we get? Well, this is 400 times 0.4. 160? Okay. Awesome.
I have another question.
What?
I have another question after we finish.
Okay, so then the rope. We know that that weighs 0.08 pounds per foot, and we have to lift it up all of that 20 feet. Okay, we've basically done this in Grecian, right? Except instead of 0.08, it was 0.8, so what's this going to be?
16?
Yes. Was that you? Or Jake? Okay. So our work is 100 foot-pounds plus 160 foot-pounds plus 16 foot-pounds for a total of 276 foot-pounds.
You added up.
Okay, I have a question.
Okay, Grayson.
So you could do this all at once. Would it, you add the 0.8 and the 0.08, or would you multiply them? You would add them, right?
But then it would just be the same.
Take the integral of 0.88 c squared.
You could do like integral
could
from
be-
0 to
yeah.
0.88 times 20 minus y plus 5.
Yes.
That's not much.
All right. And my favorite. A water tank in the shape of a cone.
No. Wednesday.
I might have done that wrong because I did fast, but I don't think that
Water Wednesday.
I did 0.88. Oh wait, oh I didn't do the. Wow.
Okay, write down what you need to. Yeah, that works. It works, Jake. You should be using a better calculator than your iPhone.
Pretty good with it.
Obviously not.
I just asked for the enter and
How am I gonna get it done? I'm not gonna be carrying a TA.
So we have a cone, and we're pumping water to a height 5 feet above the tank.
You're just gonna spill over. Like,
What?
Are we good?
We're pumping water probably into a different container.
water out of it.
I was really confused. I'm like, I'm with you.
Yeah, it's a bad. It all makes sense.
I think they're running out.
It's a.
Do we have everything written down that we need? Yeah?
It's like a cone, like,
The tank is a cone.
or like this kind of cone, but not. How do you know it's not the other kind of cone?
Well, let's think about a tank of water. It's probably gonna look like this, right?
What's the other kind of cone? Like if you put that upside down, it's just.
Yeah, that wouldn't make sense though, right? Okay, because we're like holding water, right? Okay, so here's our cone. What do we know about our cone?
It's losing water. Or gaining, I'm not sure.
There's a 5-foot straw.
There's a 5-foot straw. Okay, we'll get there in a little bit. All right, we know that we have a 2-to-8 ratio of radius to height.
That's a really good start.
Near perfect cone.
And you're perfect. If you would have got the line, just
That's all right. Okay. We are taking water in this nearly perfect cone, and we are pumping it 5 feet above.
It's gonna spill. It's gonna spill.
Guys, it's a curly straw.
it doesn't make sense.
And also. Wait, that's
Well,
a
this
big
one
straw.
actually.
Yeah, like it helps us understand.
Wait, is this still in this one?
Okay, so there's like a 5-foot pipe, or like what, 13-foot pipe that leads to some other tank, and we're pumping water out. Like, so growing up, my dad owned an ice company. Third generation business. We had to freeze water, but we had to bring water into the machines to freeze it, and then it would fall into its thing. Okay, something like that. Can you imagine that?
Sure. I like the straw.
Okay. It is a giant drinking a cup of water. And that giant has a 13-foot straw. Is this better?
Yeah, it's a normal
Okay.
person that's right
How much? What is the density of water?
Oh, wait, isn't it just one?
One.
Oh,
wait, that's for.
what I can tell you. That's.
The density of water is 62.4 pounds per cubic foot. You're probably going to need to know that. Okay. Now,
You would be expected to notice on the AP that actually probably be good for
what is the slope of that line? Okay. 4 is the slope of that line, right? So y equals 4x could be that line, okay? Well, since we're talking about everything vertically, right? Any given radius would be y over 4. Any given radius would be y over 4. Any given x length is going to be y over 4. Since that line is y equals 4x. Okay. Now, we are taking, what I want you to imagine, discs of water. And the giant is drinking it through this 13-foot straw. Okay? How do you find the area of a circle? Pi r squared. And then if we're talking about the volume, because we're talking about water, we're talking about volume, right? The volume would be pi r squared h. What? Or a disk. So we are imagining basically the very top layer of the water getting sucked out.
So that's sort of cylinder on top of.
Well, we're talking about like an infinitely thin disk of water. So pi r squared is the circle, and then it has an infinitely small thickness. Okay? And as the water drains, the shape of that circle changes because of the cone. Okay. And each disk of water weighs 62.4 pounds per cubic foot. Alright? So, we get to take that water and we get to how far? How far are we drinking it? Or the giant? So it's traveling. Whoops. It has to travel that 13 feet, so our distance is going to be 13 minus y. However, what are our limits of integration? 0 to 8, because that is where we have water. Yes. That's what I meant. Ah. Thank you. Okay? Pretty sweet, right? You will see this problem on more than one occasion.
Are we done?
With notes?
Yeah.
Yeah, we just gotta put it in our calculators. So, 62.4 pi math 9 from 0 to 8 of x squared divided by 16 times 13 minus x. So, the amount of work is 20,910.441 foot-pounds. If this happened to be in newtons and meters, then you could say joules, but then and then only, right? Joules and meters. And what? Well, the density of water would be, that would be much nicer, wouldn't it? Okay, so your homework, I don't believe you have very many problems, and I think there's like a 57 and there's really not a 57. I'm not sure which one I was trying to go for there. So I need you to do your homework. Tomorrow, I'm going to give you cups. You will fill them with water. I will give you a straw. You will drink the water and then calculate the work that it took you to drink. So we're going to...
That's tomorrow?
You don't want to do that?
I'd rather review tomorrow.
Why?
Because I'm outside.
Well, you're up.
Well, if